Hey, good afternoon. Thanks for being here in our final session. We're going to come a lot closer to home now, to the solar system, in fact, Z of 0. This is our next speaker, Dr. Laura Mayorga. Did I say that right?
It's okay.
Close enough. She got her undergrad degree at the University of Washington and PhD at New Mexico State, and is now a Future Faculty Leaders Fellow at Harvard. It's going to connect exoplanets and the solar system.
All right.
Take it away.
Thank you. So today what I want to talk about is how I've been walking this fine line between theory, observations, planetary science, and exoplanets with the goal to sort of make the connection between how local variations on planets, weather, clouds, surface features, show up and manifest in these unresolved observations that we make of exoplanets. Let me see here. Because in the solar system, it's really the only place that we can get the ground truth of what is going on and understand, in particular, direct imaging observations of exoplanets in reflected light. So there was recently, Congress mandated that the National Academy of Sciences do this exoplanet science strategy report. And one of the findings of that was that a coronagraphic or star shade-based direct imaging mission is the only path currently identified to characterize Earth-sized planets in the habitable zones of a large sample of nearby sun-like stars and reflected light. And so the recommendation of this is, of course, we need a direct imaging mission capable of measuring the reflected light spectra of these temperate Earth-like planets. Now, to get to this, there's a lot of work that we need to put in first. So the way direct imaging works is you have a coronagraph or a star shade, and it occults our host star here in the center in the simulated image from LUVOIR. And then because you are blocking the host light, or the light from the host star, these little planets around it are suddenly pop out. Now, because of the star shaded chronograph mechanism, you are never seeing the planets that are really close in, regardless of whether they're face on, like in this image, or edge on, because that's when the planets are going behind the chronographic imager. So we are never going to see these planets in direct imaging transit. We're never going to see them do a secondary eclipse. We will never see them at full phase, right? So we're always going to be seeing them partially illuminated. So direct imaging missions are biased for detecting these partial phase planets. So I'm going to talk about phase angles, and these are phase angles near 60 to 120 degrees. So the question becomes, how bright is a planet compared to its host star, particularly at these phase angles? And what is the contrast ratio, the ratio between the planet and the starlight, that we need to achieve in order to detect this planet, number one, but also be able to say something about its atmosphere, its surface, and be able to characterize it effectively. So basically what we're trying to go from is we're trying to look at this dot, which if I didn't label it Jupiter, you would have to then figure out that it actually is a planet that looks just like Jupiter, okay? And so you can see there's no resolution in this. You have color and you have a brightness, and you're trying to back out what your planet actually looks like. So just so we're all on the same page, so we're talking about phase curves. So phase curves is a measure of reflectivity as a function of phase angle. And so here's a little cartoon across the top. And I've labeled here some phase angles. So 0 is full. Out here is 90 is half illuminated. Negative 90 is just when it comes back around the other side. And so your star is somewhere in the middle of this diagram if you want to draw it in a circle. And so basically we're only going to be seeing phases sort of in this range, all right? And so what you assume for how this reflectivity varies as a function of phase angle, what equation you use, what model you use, is going to determine how bright you think those phases are. Right? So here across the bottom, this is actually a huge issue in computer vision. When we want to render objects, we want to be able to make them realistic. And so typically, what we use for planets, sort of the first guess, is the Lambertian model. The equation is shown here, where it's this ideally diffuse surface or atmosphere. And you can see a little diagram of what the sphere looks like and the surface that could produce something that looks like a Lambertian phase function. Specular reflections, we're of course all familiar with what specular reflections look like. You know, you look in the mirror, here's a surface that might be slightly more specular, and then of course you have some combination of these different things, right? So Different clouds are going to scatter a little bit differently. Different particle sizes are going to scatter a little bit differently. Different surfaces are going to scatter a little bit differently. And so in reality, these things are wavelength dependent, right? So if you look at a whiteboard in one wavelength, right, it looks sort of diffusely scattering, but in other wavelengths, it's almost like a perfect mirror, right? So what we're trying to understand is what is the actual phase curve of a real planet, and how dark are these planets going to be? So for WFIRST, LUVOIR, HabEx, all of these direct imaging missions that are coming online are trying to get down to something that can measure Jupiter or Earth. So this diagram here on the right is the contrast ratio between your host star and your planet as a function of on-sky separation, right? This is not semi-major axis, on-sky separation as it appears to us. Because your coronagraph has an inner working angle, that part that is blocked by the star shade or the coronagraph, right? That area around the star that is blocked, and an outer working angle. It has a field of view. So you're going to be limited to somewhere between, say, 0.1 arc seconds or so, or 0.3, I think is somewhere in that range for WFIRST and these other big flagship missions. And then depending on how good your technology, what you can get down to, right? I think WFIRST is aiming for somewhere down here times 10 to the minus 9, and LUVOIR is trying to go somewhere 10 to the minus 10. And so you can see here, we have a smattering of already direct imaging planets we've discovered. Famous ones include HR 8799 system, but these are young hot planets, right? So we're looking at them in emission. This is not reflected light. So we need to get down to planets down here. These are a bunch of rate of velocity discovered planets. 55 concrete system is in here, and you can see we're aiming for Jupiter here. These curves are just sort of a representation, if they were Lambertian spheres, of how their brightness would vary throughout their orbit. So we want to figure out how bright do we, or how precisely do we need to get down in order to characterize these planets. So it's going to be dependent on the constituents in the atmosphere or surface that make up the disk of your planet that you're observing. So reflected light is a particularly powerful way of measuring a planet's atmosphere because it's sensitive to scattering properties from multiple places in the atmosphere. So not just single scattering, but multiple scattering. And so that reflected light signal you get is imprinted with multiple layers of atmospheric information. So you can back up things like atmospheric structure, the temperature, pressure profile, the composition. And of course, brighter planets are easier to detect, so we're hoping that there's a lot of bright planets out there. And the unresolved surface features on terrestrial planets, for example, will contribute to the reflected light of the planet, which will vary as a function of planet rotation and as illumination. So this is an extra complexity for terrestrial planets. So before we get to terrestrial planets, let's use giant planets as a stepping stone, because the techniques that we develop for giant planets are what we're going to use and get tested first before we actually start measuring these terrestrial planets. So from the ground, for Jupiter, we can only see about to 12 degrees phase. And this is about 6 degrees for Saturn, and it gets worse as you go out. Because you need to be outside of that planet's orbit in order to get these kinds of phase angles. So luckily for us, and what this image here at the bottom shows, is data from the Cassini flyby of Jupiter. So Cassini did a flyby on its way to Saturn of Jupiter in late 2000, early 2001, and the data I'm using here from the Imaging Science subsystem. So this was 2 cameras, a wide-angle camera and a narrow-angle camera that had about 18 to 24 filters between them, and I'm just going to show you results from 6 of those filters to sort of maximize what phase coverage I was able to get. So up here at the top, you can see just what those filters actually cover, their band passes. And here across the bottom, you can see sort of the flight path and where the 2 cameras were taking images, just offset for clarity. And then a little postage stamp here of just sort of false color, just to give you an idea of what Jupiter looks like in all of these different filters. So here are some results. I'm just showing you sort of 2 filters right now. So blue, a very blue filter, and CV2, which is a continuum filter out in the red. And so the black and gray points here are from those 2 different cameras. And so we've calibrated them, so of course they give you the same answer. And this blue line here is just a 5th order polynomial to sort of guide your eye of what's going on here. And we can compare this to a variety of models and see how well we're actually doing. So of course, first, you want to compare it to the Lambertian model, that first guess that we all reach for. Jupiter is not Lambertian. So first off, you can see that in sort of this phase angle range that we care about, the sort of 60 to 120 degrees, in some places, Jupiter is actually significantly darker than this Lambertian model is predicting. On top of that, here at these low phase angles, right, this part that we can sort of start to see from the ground, there is a significant difference in the shape of the phase curve. Now, in Jupiter's atmosphere, this sort of this peakiness, this cuspiness, this what we call the opposition effect in planetary science, is caused by these large particles in Jupiter's upper atmosphere that are very strongly backscattering, right? And so they give this sort of appearance of sort of a very specular reflection. Now, this is something that we have not observed in exoplanets and have yet to observe, and I don't think we will ever be able to observe because this is roughly where your transits are. Right? We can compare this to other simple models. So what I've added here are, if you assume that Jupiter was a purely Rayleigh scattering sphere, which is not true because it has clouds, it is not clear. And this is just 3 models with different single scattering albedos, and so you can see how well they're doing. It's okay. And then you can see here with this model from Cahoy et al., it is a Jupiter-like exoplanet model. When I say Jupiter-like, what I mean is that it's got a route about Jupiter's metallicity, it's about a sun-like star, it's about kind of the right distance to sort of match Jupiter. And you can see that's this sort of brownish line here. Where'd my mouse go? This brownish line here. That it's actually doing a particularly good job in these redder filters. In the blue, it's not so good, but this is actually because it's missing some of that photochemistry that is going on in Jupiter's upper atmosphere that is particularly important in these blue wavelengths in order to keep the reflectivity high. And so you can see that we're doing actually a pretty good job with some of these models. Now that's giant planets. We want to step down to terrestrial planets. Now looking for us in the solar system, we have a variety of planet analogs that we can use to try to understand exoplanets. And in this case, what I'm talking about is the Galilean satellites. Now, it just so happened that in this data set from Cassini, we have an image here from the narrow angle camera and an image here from the wide angle camera, that occasionally the Galilean satellites sort of appeared in the background and the foreground of these images. Now, I want to be clear here, I'm not talking about exomoons. What I'm talking about is, despite their similar sizes and densities of the Galilean satellites, their similar temperatures, they have a variety of surfaces, and they represent a potential, from their different formation scenarios and evolution histories, a variety, a sample, if you will, of potential surfaces that exoplanets could have. And so in studying these, we can start to get a handle on the rotational and illumination variations of terrestrial planets. And so it's a complicated problem, right? We have rotational variations that we're trying to model. We have illumination variations that we're trying to model. So I took from those images, we throw out all the resolution just like before, and we make disk integrated observations. And what we're trying to do is fit the illumination variations at the same time as we fit these rotational variations, right? So this rotational variations are actually all this extra noise here in this phase curve. And so we sort of go back and forth, fitting the rotational variations out, and then fitting the phase curve variations again, until we sort of converge on a final solution that fits both. Then from that, we can actually invert these rotational variations to produce a brightness map. So in this way, we're actually getting additional information about this pretend exoplanet. And this could be a mechanism we could use to actually start to resolve these we'll never be able to resolve exoplanets. So this is our first baby steps to actually trying to map out an exoplanet in direct imaging. We can then compare these resolved maps to the real thing, because in some ways, planetary science is way, way ahead of exoplanet science. We've been directly imaging planets in the solar system for hundreds of years. In other ways, exoplanets is a little bit ahead. But here we can see how well this very basic, very simplistic model is doing compared to our actual resolved maps of the moons. And so we can make comparison between these two things. We can measure the color variations, and then we can pretend that these are now Earth-sized planets with these surfaces on them, and get an idea of what the contrast ratios we are going to need to reach in order to be able to study them. And so here on the very bottom right, what I'm showing is just a comparison of these 6 slices that we used here in these maps and how well they're doing. I should say that these maps I'm using are from the USGS astrogeologic program, and they are mosaics of Voyager and Galileo data taken in a variety of filters with a variety of different phase angles. So they're not perfect apples to apples comparisons. And so, for example, in this case, where the peak seems to be happening at sort of a reasonable comparative location, and the minimum is happening, is great in the same spot. We're happy with this. So you'll be seeing a lot of these rotational curves, right? So the reflectivity, longitude maps. These are the corresponding brightness maps we make with our simplistic model in this next few slides. So just to prime you for that. So we have 4 objects. Our first object is Io. Now Io is a very active moon. Its surface is covered in sulfate and sulfur deposits that can cause from the volcanic activity, and it has very interesting interactions with Jupiter's magnetic field. And so we can see here, I have showing 3 of the filters, so violet, green, and something that's kind of red. We have reflectivity as a function of longitude. And from this brightness model, or brightness map model, we can fit these reflectivity variations, and what you're seeing here in these bottom panels are the residuals from those fits. Okay? And we can measure the variation here. And so in violet, this is actually where we're getting the most variation of Io's surface as proportional variations, right? So this is basically the max and min difference from the mean. You can also see in these curves that the shape of the rotational variations is changing, and it's actually obvious to your eye. And so this implies that there is significant color variation of Io as a function of rotation. So here are the 3 maps that we produce from these fits, and here is the USGS astrogeologic map, which we then slice up to compare. And so since it's predominantly, these are taken in a clear filter, and then occasionally other filters were included to sort of fill out the map and try to increase resolution. I just simply do a linear combination across these 2 filters for comparison, right? So this is why I'm saying the max is almost in the right spot, the min is almost in the right spot, the shape's almost right. Like we're doing pretty good. This is okay. So that's Io, Europa. Europa here, you can see that the shape is actually pretty consistent. It looks fairly sinusoidal across all the different filters. Violet is again still the source of our largest variations. There's across the middle there, you can see that the one hemisphere is particularly much brighter than the other hemisphere, as implied from the rotational light curves we have here. And then from the map, you can see that that's pretty much also the same case, right? So we have this sort of roughed up hemisphere on Europa. It's all icy covered with these big crevasses that have opened up sort of over time. And here's the slice brightness comparison again. It's okay. Ganymede. Ganymede is an interesting moon in the sense that it's one of the only moons that has a magnetic field, actually. So that sort of makes it particularly unique. It has, rather than that sinusoidal pattern we saw earlier on Europa, it's got sort of this really bright hemisphere and sort of, maybe there's variation in there, maybe there isn't. Here are the maps that we reproduced from that compared to the astrogeologic map. You'll note that it's pretty consistent across, amplitude-wise, across all the filters in rotation for the rotational variations. So that sort of doesn't imply too much about color variations later, but we'll get to those in a minute. Callisto. So Callisto is the furthest out, which means it was the one that was least caught in the data set. It was usually outside of the field of view of both of the cameras, or behind Jupiter, or in front of Jupiter, in which case I couldn't use it for this study. And so it's a bit of a problem child because it has lots of noise, but it also has the least amount of data. And so we see some interesting things here. So from the rotational light curves that we measure, it seems to imply that this hemisphere, right here around longitude 90, is actually the brighter hemisphere. From the map, that seems to be the opposite case. Now, if you look at the slice brightness comparison, you can actually see that this is the where we predict it to be a lot brighter, but everything else besides this anomaly is actually the exact same shape. And if you look at this map and you sort of squint at it, I mean, there is actually a resolution difference in the map between this hemisphere and this hemisphere. And so maybe this is real. And besides that, though, and whatever discrepancy we have here, the rest of it seems to be behaving identically, right? The same little stair step here. But for some reason, perhaps it's the map, perhaps it's the data, but you'd be hard-pressed to convince me it's not the data that hemisphere is supposed to be brighter. So just sort of summarize here in the same way that we did for Jupiter. Right here now I'm showing the contrast ratio instead of the actual phase curves as a function of phase angle for all 4 of the moons. So if we just focus on the brown line here for Io, here's if we assume that Io is an Earth-like exoplanet around at 1 AU from a sun-like star, this would be the contrast ratio that you would get if it was full, right? So that's 10 to the minus 9 right there. And then it's pretty steep again. It doesn't have that nice little, this is Lambertian light here, it doesn't have that same little nice flattening at the top. It's very cuspy. This is the opposition effect again. And note that all of them have it, right? In comparison, you can see that all of them are much, much darker. So for Jupiter, right, depending on which filter we were looking at, it was about 10 to 25% darker. I think in CB3, it's like almost 50% darker Jupiter. CB3 is kind of a tough filter, though. But here, these are all about 50% darker in the phase angle range that we're predominantly going to be measuring with direct imaging here, the 60 to 120. Now, this is terrifying. You should all be terrified, right? Because LUVOIR was aiming for 10 to the minus 10, right? Which is here, maybe, right? We're aiming for a few 10 to the minus 10. We're barely going to be able to detect these, right? These are really tough contrast ratios. The width here, these shaded regions, are the rotational variations that we were measuring before, that percentage, that's sort of that band that it could vary based on the surface variations. And you can see if we wanted to detect those, right, we'd have to go even an order of magnitude higher in our precision, right? So, and then if the surface is Callisto, then, you know, that's really, really dark. Now, those assume that the rotational variations that I'm measuring, which are at roughly 15 to 25 degrees phase angles is where those rotational light curves were, that assumes that that is true across the whole illumination phase, right? We're trying to separate rotation and illumination phase here. And so the ones I was showing you were basically when the moon is almost full. Now I have very, very little data out at high phase angles, and so it's difficult to make the same rotational curve for all the moons, but you can manage it for Io in green. And so here what I'm showing you is at higher phase angles, and I have to cheat a little, I have to use a much larger phase angle range. So this is very, we can suspect this is true, but it's hard to say it's true without additional data. But this is the rotational light curve we measure if I use everything from 98 degrees and onwards, right? So the shape is completely different. The proportional variation of these changes is higher, which is something you'd expect. You'd expect that if you were in a very crescent phase, any little variations in the surface brightness, of course, have a much proportionally larger effect on what you're measuring. Whereas if you have you're measuring it at full phase, right, then everything sort of gets muddied out. And so you can see that even though these phase angle, the rotational variations at these phase angles could be proportionally much higher, this is still a really faint object that you're trying to detect and characterize. But it's really interesting that the shape of this is different, right? Because that implies that there's a difference in the way that rotationally the color of this object will vary as well at higher illumination phase. Now, if you are a 90s kid, or raised a 90s kid, then you are very concerned about being tricked by things, right? And what I've been talking about is how, so far, how light can trick us from the very perspective that we use it into thinking that our objects are something else, or that they're actually going to be a lot darker than we think they are, right? And so if you were a 90s kid and you were watching this episode when it aired, you were like, I know what it is. It's Voltorb. And then you never played this game again because it was actually Electrode and you were tricked, right? And so what I'm worried about is I want to make sure that when we observe these planets, we actually know what we're looking at, right? Because this is really hard. I have a couple minutes left. So we're going to play a game. We have made this observation, and it's low resolution. Normally I would show it really small, right, to actually be relative. And we're going to guess, who's that dog? All right, so raise your hand if you think it's number 1, Alana. Okay. Raise your hand if you think it's Emmy. No, thanks. One, okay. Pearl. A couple of you think it's Pearl. It's Alana. That's Courtney Dressing's new puppy. All right, here's another one. Who's that dog? Is it Dante? Hands for Dante. Is it Loki? Is it actually Misto the cat? It's Misto the cat. It's tough, right? Because you can't just use color alone to make these classifications, right? Because it actually turns out you can't tell in this picture of Misto, but Misto's belly is actually white. And just like in that Voltorb Electrode example I showed, it's not uncommon for when you look at an object in one perspective that it's actually completely different than when you look at it in the other perspective. So here's just a smattering of pets showing how their undersides are different colors than their backs. This is my cat, by the way. And so the danger here of trying to use color as a classifier, there was some thoughts for a while that we could try to use this to differentiate giant planets and terrestrial planets from like background stars and background brown dwarfs and these kinds of images. But the danger is that the color of the planet you're detecting may not actually be what you're expecting if you're using these ground-based full-phase information of the planets in our solar system. Because from that single snapshot, from that direct imaging observation you made, you're trying to classify and figure out what kind of atmospheric properties this planet has. And so what I'm showing here is there was that Cahoy et al. Model before, right, that was doing a pretty good job of fitting the phase curve of Jupiter. And this is what the data actually suggest, right, this curve here. And I've color-coded it as a function of phase angle, right? So remember, we're looking for something between 60 and 120. That's sort of our region of interest. A Jupiter twin at 90, which is this pink section here, is a different color, right, than Jupiter at full phase. Not only that, but this variation is so much larger than what we were predicting with models, right? You can look at the same things for the Galilean satellites. Now, since I have rotational information for those as well as illumination variation, we can do the color in both ways. So this is a little bit of a complicated diagram, but we'll step through it slowly. So on the left here, we have their variations as a function of illumination, okay? And these are all on the exact same scale, right? And rather than laying them on top of each other, I've just split them up so you can actually see how, fortunately for us, even though the colors of Callisto, Ganymede, and Europa are very similar in color space, they all vary differently with phase angle. And so we will be able to tell them apart as long as you can get this color information. Europa is actually, or sorry, not Europa, Io is a different color completely, and so that'll actually be really good for us in figuring out Io's volcanic worlds, right, from these icy terrestrial type objects. Here are just zoom-ins of these critical regions here of where I have that rotational information. So these lines here are now the variations in color with rotation. Now, because of our very simplistic model fitting and the quality of our data, these ellipses here are actually showing the errors that we can make for our measurements of color variations. And so unfortunately, except for Io, these are all, the rotational color variations are consistent with our noise. So coming back to this idea that when you look at a planet from one perspective, it looks different from a different perspective, right? I showed you what color variations we could measure from the equator, right? From in the plane, that's where we have all our observations of in the solar system. Until recently, when Juno This lovely picture is from the JunoCam imager aboard Juno. Got to Jupiter, we finally left the plane. The Cassini end of mission orbits, of course, also got above the plane of Saturn right before Cassini died. So we all saw images like this and we were all amazed, right? I'm sure all of you oohed and awed in your office when you first saw it, because there's this great complexity in the cloud structures. And we're being able to use things like the shadows to figure out how high some of these clouds are actually in the atmosphere. But I looked at this image with a dawning horror and terror, because Jupiter's pole is blue, right? Now from the equator, we look at Jupiter and it's, red and white, and people argue over whether something's burnt orange or butterscotch. But that's blue. So really, in that LUVOIR image, should Jupiter actually be blue instead of sort of that yellow color? The danger in interpreting that kind of information from this image is that JunoCam is an outreach camera, which means that it isn't actually calibrated sufficiently to do science image with it. It's not even flat-fielded. My goal is to hopefully be able to do something with that data, maybe reduce it, use some of the star images they used to actually make these images science-worthy. Because it's these kinds of perspectives that are critical, that we actually need in order to say anything about what kind of giant planets are like in direct imaging. Now, we know from equatorial observations of these planets that there are temporal variations in their color. So for example, on Saturn's pole, the hexagon, it's changed color multiple times. We've observed that, right? It's gone yellow and it's gone back to white and it's changed. There are transient storms, of course, on all of these planets that will change the reflectivity. And we need to understand those so that we actually measure and take these observations of direct imaging, which may happen in 100 years or sooner, that we're actually going to be able to understand what we're looking at. How much time? A couple minutes. So maybe this will take 100 years, maybe this won't take 100 years. But there's a lot of questions that we still have to answer before we're actually ready to understand direct imaging missions. And I was going to go off into a little modeling tangent and tell you how I was trying to answer some of these questions with our modeling efforts, right, for something we could do a little bit in the future. Because what's the interesting thing about reflected light observations is that not everything is capable of measuring reflected light. There's actually a danger that in the future we're becoming more and more insensitive to blue light. Typically, the phase curve studies that you've seen are done in thermal emission. And this is actually going to become more and more often the case, because what we're using to do those studies are transit method surveys, right? And as they've been moving towards, we're looking for these smaller and smaller planets, right? We're targeting smaller and smaller stars, which are very red. And so we've sort of been leaning into this much redder bandpass, which means, though, that we won't be able to measure reflected light as well. And so one of the recent things I've done is done some modeling about what kinds of planets are we actually able to probe with reflected light in this new era brought to us by TESS and the beyond missions of that, and what kind of atmospheric properties do they have? Because not only do we not understand polar perspectives of our planets, we don't even know what effect rings have, right? Saturn's rings, what do they look like from the poles? What about if they have slightly different cloud compositions, right? The types of clouds that we're actually going to be able to measure in reflected light at these, for when they're cool enough not to have thermal emission in your bandpass, for example, are completely different kinds of clouds that we're actually measuring right now in the solar system, right? These are much hotter planets that you get from out of transit surveys, and so they're kind of a completely different class than what we're doing with direct imaging. But I'm out of time, so I'll just end there. No? Okay, I can keep going. This next section is a little bit long. So in reality, what I'm going to do is you should ask me about the greatest slide that I've ever made, if you want to hear more about that. Okay. I have lots of great puns and references you can make with that. But basically, the takeaway point from that is that the types of clouds you have in your atmosphere will drastically change your reflected light spectrum from this, right? So what I'm showing you here is just for one of these planets that could potentially be observed by TESS that is cool enough that it won't have thermal contamination. unless you stick the smallest particle cloud and you loft it way up high in the atmosphere, which is basically the smallest FSEDs in this diagram, you won't be able to measure any reflected light from any planet with tests. And so here what you're seeing is the contrast ratio. For Kepler, you could get down to like a part per million, for example. TESS, the noise floor is at about 30 parts per million or so. And so in comparison to like a blue filter, right, you can imagine, you can remember what Kepler's bandpass was. It was very wide, but it was also very blue. And so the peak of all sort of the reflected light happens right here, where Rayleigh scattering is predominantly is dominating, right? And so this blue wavelength range is really important to protect if you want to actually study reflected light in exoplanets and sort of make that connection to that direct imaging space that we're going to need to be able to understand for the future. So with that, I'll just show you sort of other scary diagram of contrast curves for the variety of cloud classes and a bunch of future transit survey surveys that are coming online. You can see tests, yeah. Right, Kepler was okay because it was very, very precise, right? So for these kinds of planets, you need very, very high precision instrumentation. So to summarize, planets aren't Lambertian. So they are going to be much, much darker than we are predicting them to be. Jupiter, 25%. Galilean satellites, or anything that has a surface like a Galilean satellite, 50% darker, right? So all those planets I showed you in that first diagram that was planetary, the contrast by angular separation, much darker. If we pretend the Galilean satellites are like worlds, right, we're actually shooting for 10 to the minus 11 contrast ratios. These color variations that you can get are quite large, and we can actually use them to tell surfaces apart. So that's nice, but again, they can trick us into misclassifying our exoplanets. There is some hint in my data, minimal data, that can suggest that these rotational variations are, of course, much proportionally larger at higher phase angles, but I need more in order to say that actually is true. And that contrast ratios are more favorable for the detection of reflected light at bluer wavelengths, which is something that we could lose in future missions, unless we have basically the golden case of Neptune, very, very close to its host star, right? These are commonly M dwarfs, stars in these surveys with very small, high lofted cloud particles. That's what you're going to get. Thanks.
Thank you, Laura. An excellent and scary talk. Question here.
How will the European JUICE mission help with the resolution maps of the Galilean moons? Would that be something useful?
Do you remember what JUICE's orbit is?
I don't remember what the orbit is. It's a very orbit.
Is it equatorial or is it?
Yeah, I think it's going to get different phase angles. I think that's one of the points.
Yeah. So I don't remember the particulars of JUICE's instrumentation, but if it is going to get much higher resolution maps, then I would be concerned about what the solar illumination angle is when they take those observations, right? So for example, a lot of our Mars data is taken at exactly 3 p.m. everywhere on the planet, which is nice for comparing different surfaces across the whole planet and for actually building a map that's at one illumination phase angle, but that won't necessarily be the case in this scenario, because it'll be opening Jupiter, not actually one of the satellites. So pros and cons there.
And another question is, none of those satellites have atmospheres.
That's not actually true.
Stable, sustained, consistent atmospheres like the Earth or Venus.
I'll give you they're not like Earth and Venus.
How would that change? Because we expect if they're slightly larger or something, that's an atmosphere is going to very much change this.
Yes.
For exoplanets, have you looked into how an atmosphere would help? Would it make it better or would it make it worse?
So part of the reason I started this is because I was worried, right, that we would try to measure an atmosphere on a terrestrial planet and we would instead be measuring something on the surface instead, right? And so there's been a lot of studies done with Earth's phase curve, looking at how the surface variations of the oceans and continents affect the reflected light signal you get from Earth. And we've only recently started to actually paint on Earth's clouds in that study, right? And so it really comes down to how opaque is your atmosphere, right? And what the clouds are doing. Because for example, in hurricane season, right, there's gonna be just this, they're fairly slow moving in the grand scheme of things, hurricanes, but they're gonna be this one bright spot on the planet, right? But it actually turns out that the majority of the reflected light variation is caused by ocean glint on the Earth and actually by Australia. And it's not so much dominated by what's going on with the weather patterns. But that is a concern.
Other questions?
So I have a question about the scare part of the color variations. So it seems like part of that, like possible biases might be coming from us not modeling all of what's going on. But in the models that you showed for the Jupiter level, their exoplanet, there was color variation as a function of like angles. So I missed where that was coming from.
Yeah, so the most important thing missing from that model is that photochemistry in the blue, right? And so the blue bit that's missing would probably be what actually drives that into the other direction, because it's sort of like a hook down, right? Whereas all the variation is sort of up to the upper right. That's sort of going to do that. But the assumptions that they make into how they're, because like the spectrum, you can, sorry, let me back up. You can plot the Cahoy et al. Model spectrum and compare it to the albedo spectrum we have of Jupiter. And it's a pretty good match, except for in that very, very blue corner. It's supposed to kind of stay flat, and the model kind of turns down. So when you then on top of that, right, you are then making an assumption when you compute the phase angle variation of what that albedo spectrum is, right? Classically, you could potentially assume it's a Lambertian and just scale the whole thing up and down, right? They do better than that, but still that scaling isn't quite right, right? Because you can see in the phase curve that it's not quite right when I filter integrate it to match my filter. And so the blue, that photochemistry stuff that's missing, is part of what's driving the fact that it's in the wrong direction. That magnitude comes down to how they're actually doing the phase curve that they get from that and what they're assuming for the actual scattering of what's going on in their atmosphere, right? Because it's not perfect. So that's what's driving that.
One more question? I'll ask one. So Cassini flew by Jupiter, but it hung out at Saturn for a long time.
Mm-hmm.
Is there data from there that you can use?
Yeah, so there actually was a study done by Uliana Diudina in 2 papers where she looked at the variations in illumination with Saturn, and it's done in a little bit more of the planetary science kind of way. And so we talk about like Haney-Greenstein parameters and stuff like that, but basically it all boils down to doing a phase curve. But nobody has included Saturn's rings in their study. They're really more worried about what the atmosphere is doing. And so the scattering of the rings, I think, is going to be particularly important to go back and re-include, especially for the Cassini end of mission orbits.
Thanks. Thank you, Laura.